Have you ever looked up at the night sky and wondered about those tiny points of light? Some of them are stars, massive balls of burning gas light years away. Others, however, are closer to home. These are satellites, sophisticated machines orbiting our planet, silently shaping our modern world. Satellites have revolutionized the way we live, work, and connect with each other. They have become an indispensable part of our daily lives, even if we don't always realize it. From communication and navigation to weather forecasting and disaster management, these technological marvels have touched every aspect of our existence. But how do these feats of engineering actually work? How do they stay up in space? And what role do they play in our increasingly interconnected world? In this exploration, we'll delve into the fascinating world of satellites, uncovering the science behind their operation and their profound impact on our lives. Fasten your seatbelts as we embark on a journey to unravel the mysteries of these silent guardians orbiting above. Satellites come in various shapes and sizes, each designed for a specific purpose. These incredible machines orbit our planet, providing a wide array of services that are integral to modern life. They can be broadly categorized based on their function, orbiting altitude, and the type of data they collect and transmit. This categorization helps in understanding the diverse roles satellites play in our daily lives. Communication satellites, as their name suggests, facilitate communication over long distances. These satellites are the backbone of global communication networks. They act as relays, receiving signals from ground stations on Earth and transmitting them back to different locations. This process ensures that information can be shared across continents in real time. This enables everything from satellite TV and internet services to long-distance phone calls and video conferencing. Without communication satellites, our ability to connect with others around the world would be severely limited. Navigation satellites, like those comprising the Global Positioning System, provide location and time information to users on the ground, in the air, or at sea. These satellites are essential for modern navigation. These satellites constantly transmit signals that allow receivers to determine their precise location, enabling navigation, mapping, and surveying applications. From finding the quickest route to a destination to conducting geological surveys, navigation satellites are indispensable. Weather satellites equipped with specialized sensors monitor Earth's atmosphere and surface, providing crucial data for weather forecasting, climate monitoring, and environmental studies. They play a vital role in predicting weather patterns and natural disasters. They capture images of cloud formations, track storms and hurricanes, and measure temperature, humidity, and other atmospheric conditions. This data is essential for meteorologists to provide accurate weather forecasts and warnings. Scientific satellites are designed for a wide range of research purposes, from studying the Earth's magnetic field and gravity to observing distant stars and galaxies. These satellites expand our understanding of the universe. They carry sophisticated instruments to collect data and transmit it back to Earth for analysis by scientists. This data helps in making groundbreaking discoveries and advancing scientific knowledge. From understanding climate change to exploring the far reaches of space, scientific satellites are at the forefront of discovery. Earth observation satellites are another crucial category. These satellites capture high-resolution images of our planet, which are used for a variety of applications, including environmental monitoring, urban planning, and agriculture. By analyzing these images, scientists and researchers can monitor deforestation, track urban development, and assess crop health. This information is vital for sustainable development and environmental conservation. Military satellites, on the other hand, are used for defense and intelligence purposes. They provide secure communication channels, monitor military operations, and gather intelligence data. These satellites ensure that military forces can communicate securely and effectively, and they play a critical role in national security. The data they provide is often encrypted to prevent unauthorized access. In summary, satellites are indispensable tools that serve a multitude of purposes. From enabling global communication and navigation to advancing scientific research and ensuring national security, their applications are vast and varied. As technology continues to evolve, the capabilities and importance of satellites will only continue to grow. The story of satellites began on October 4, 1957, with the launch of Sputnik 1 by the Soviet Union. This small spherical satellite, the first artificial object to orbit Earth, marked the dawn of the space age and ignited a space race between the Soviet Union and the United States. Sputnik 1, though simple in design, had a profound impact on human history. It demonstrated the feasibility of spaceflight and ushered in an era of unprecedented technological advancement. The success of Sputnik 1 spurred both superpowers to invest heavily in space exploration, leading to rapid advancements in rocketry, satellite technology, and our understanding of the cosmos. Following Sputnik 1, a flurry of satellites followed, each more sophisticated than its predecessor. Early satellites were primarily focused on scientific research and military applications. However, as technology progressed, satellites found applications in a wide range of fields, transforming communication, navigation, weather forecasting, and our understanding of our own planet. Section 4. Launching into the cosmos, a rocket's journey. Launching a satellite into orbit is a complex and challenging endeavor, requiring immense power, precision, and coordination. It all begins with a rocket, a towering structure designed to overcome Earth's gravitational pull and carry the satellite beyond the atmosphere. Rockets like the Falcon 9, developed by SpaceX, are powered by powerful engines that burn a mixture of fuel and oxidizer to produce thrust. The immense force generated by these engines propels the rocket upward, overcoming the downward pull of gravity. As the rocket ascends through the atmosphere, it sheds stages in a carefully choreographed sequence. Each stage is jettisoned once its fuel is depleted, reducing the weight of the rocket and allowing it to accelerate faster. The final stage carries the satellite to its intended orbit. The launch process is a delicate balancing act requiring precise calculations and adjustments to ensure the satellite reaches its intended orbit safely and efficiently. Any deviation from the planned trajectory could result in the satellite being lost in space, or worse, falling back to Earth. Section 5. Finding their place, different types of orbits. Once a satellite is launched into space, it doesn't simply float aimlessly. Instead, it follows a meticulously planned trajectory. This trajectory is known as an orbit, a specific path that the satellite follows around Earth. Orbits are crucial for ensuring that satellites serve their intended purposes effectively. The type of orbit a satellite is placed in depends on its mission and the coverage area required. Different orbits offer unique advantages and are chosen based on the satellite's function. Low Earth orbit, or LEO, is a region of space located between 160 and 2,000 kilometers above Earth's surface. This is the closest orbit to Earth and is often used for a variety of applications. Satellites in LEO orbit the planet quickly, completing one orbit every 90 minutes to 2 hours. This rapid movement allows them to cover the entire Earth multiple times a day. This proximity to Earth makes them suitable for applications requiring high resolution and low latency, such as Earth observation, remote sensing, and communication. For instance, Earth observation satellites can capture detailed images of the planet's surface, which are invaluable for environmental monitoring and disaster management. Medium Earth orbit, or MEO, lies between LEO and GEO at an altitude of roughly 2,000 to 36,000 kilometers. This intermediate orbit offers a balance between coverage area and signal latency. Satellites in MEO orbit Earth at a slower pace than those in LEO, taking several hours to complete one orbit. This slower pace allows for more stable and consistent coverage over larger areas. This makes them well suited for navigation systems like GPS, which require global coverage and moderate signal latency. GPS satellites in MEO provide the precise positioning data that is essential for navigation and timing services worldwide. Geostationary orbit, or GEO, is a circular orbit situated directly above Earth's equator at an altitude of approximately 36,000 kilometers. This high altitude allows satellites to have a wide field of view, covering nearly a third of the Earth's surface. Satellites in GEO orbit Earth at the same rate that the planet rotates, making them appear stationary from the ground. This means that a satellite in GEO will always be positioned over the same spot on Earth, providing continuous coverage to that area. This unique characteristic makes GEO ideal for communication satellites, as it allows them to provide continuous coverage to a specific region on Earth. This is particularly useful for television broadcasting, weather monitoring, and other services that require a constant connection. Each type of orbit has its own set of advantages and is chosen based on the specific needs of the satellite's mission. Understanding these different orbits helps us appreciate the complexity and precision involved in satellite operations. From the control centers on Earth to the satellites orbiting above, every aspect of satellite deployment and operation is meticulously planned to ensure optimal performance and coverage. As we continue to rely on satellites for communication, navigation, and observation, the importance of understanding and utilizing different types of orbits becomes ever more critical. These orbits are the invisible highways that keep our modern world connected and informed. Section 6. The Dance of Gravity. How satellites stay up. Satellites stay in orbit thanks to a delicate balance between gravity and inertia. This balance is a fascinating dance that allows these man-made objects to circle our planet without falling back to the ground or drifting off into space. Gravity, the force that attracts objects with mass, constantly pulls the satellite towards Earth. This force is what keeps the satellite from flying off into the vastness of space. Inertia, on the other hand, is the tendency of an object in motion to stay in motion at a constant speed and in a straight line unless acted upon by an external force. This principle is crucial for understanding how satellites maintain their orbits. To understand how this balance works, imagine throwing a ball horizontally. The ball would travel forward due to its inertia, but would also curve downward due to gravity, eventually hitting the ground. The ball would travel forward due to its inertia, but would also curve downward due to gravity, eventually hitting the ground. This is because gravity is constantly pulling it downwards. The faster you throw the ball, the farther it travels before hitting the ground. This is because its horizontal velocity is greater, allowing it to cover more distance before gravity pulls it down. Now, imagine throwing the ball so fast that its horizontal velocity is sufficient to counterbalance the downward pull of gravity. In this scenario, the ball would continue to fall towards the Earth, but its forward motion would keep it from hitting the ground. The ball would still curve downward due to gravity, but the curvature of its path would match the curvature of Earth. This means that as the ball falls, the Earth curves away beneath it. In essence, the ball would be in orbit. It would be falling towards Earth, but because of its high horizontal speed, it would keep missing the ground, creating a continuous loop around the planet. Satellites work in a similar way. They are launched into space with a powerful rocket that gives them the necessary speed to achieve orbit. They are launched into orbit with enough horizontal velocity to counterbalance the downward pull of gravity. This precise speed is what allows them to stay in orbit without falling back to Earth or drifting away. This constant interplay between gravity and inertia keeps the satellite in a stable orbit, allowing it to circle Earth without falling back down. It's a delicate balance that requires precise calculations and careful planning to achieve. Once in orbit, satellites can perform a variety of functions, from transmitting signals for communication to capturing images of our planet. Their ability to stay in orbit is what makes these tasks possible. The science behind how satellites stay up is a testament to human ingenuity and our understanding of the laws of physics. It's a perfect example of how we can harness natural forces to achieve incredible feats. Stay curious and keep exploring the digital world.